A gap that has emerged in terms of understanding whole systems behaving animals is that quite often animals are both solving the problem of a mechanical problem of getting the body over to a particular point in space, as well as acquiring information. And how these two things can fit together is a bit of a puzzle, because sometimes they are strongly at odds. And just as a simple example, if you move a visual system through space beyond a certain velocity, basically the integration time over the acceptance angle of a photoreceptor, then you have blur. And blur is a really significant problem, to the point that we have this super special circuit called the VOR, which does stabilization of our eyes without us even knowing it. But many other animals don't even have that circuit, and they have to run, stop, look at what they're going to next do, run again, stop, and look at what they're next going to do. So there's this possible tension, in many cases, between movement and acquiring sensory information. I'm going to tell you a story about this guy, which is a weakly electric fish from the Amazon River. They're nocturnal fish. They hunt in complete darkness in murky waters of the Amazon. And I'm going to tell you how we can understand a behavior that would be completely perplexing if you look at it from an information acquisition standpoint, or exclusively from a mechanics standpoint. But once you join the two of these together, it actually fits together beautifully. So this is a cheap powered speaker, and I'm just dropping the leads of the speaker into the tank. The animal is emitting a weak electric field in the range of 50 hertz to 2 kilohertz, depending on the species. It's fixed to a species typical range, and the species are sometimes non-overlapping. If two individuals come up to each other in the murky water, they will shift frequencies so they're not interfering with one another's discharges. So that's the electric field. They're very weak fields. They're not like strongly electric eels that you might be familiar with. You can't sense the electric field. Now here's the behavior I want to start off with. This is an infrared video of a search and strike of Daphnia magna, which is a 2 millimeter long water flea that they like to hunt in their native environment. Here's a top view, here's a side view. This is going to go by very quickly. You can just look at the top view for now. There's the prey, that red dot, and you see that it detects the prey completely in the dark near its tail and does this rapid reversal. It has a bidirectional, and I'll show later, multi-directional locomotory system. Now look at the side view. See this pitch in the body. It's a little subtle, and it took a little while to really see the significance of this. But if you look at over a bunch of different behaviors, you actually see over 100 trials that that's a 30-degree angle. And this is very perplexing. From a fluid dynamics perspective, this is a very costly thing for an animal to be doing in a fluid. So 30 degrees. How does this behavior affect movement energetics is the first question I'm going to address. And then I'm going to address how does this behavior affect information acquisition bit rate. So the first thing we need to know is how does body pitch affect the amount of force that you need to push the body with to get through the fluid. There's a few different ways of doing this. We've done both empirical and computing with fully resolved 3D Navier-Stokes on a supercomputer. I'm going to show you the supercomputer results, which are quite similar to the empirical results. You pitch the body and swim it in the computer at different angles, and you measure the drag force at different velocities, and this is what you get out. All right, and we did the empirical thing, and it also worked. Some snapshots of the simulations show why these forces go up as the body pitches. It has to do with separation of flow at increased pitches, and you have nicely laminar flow at lower pitches. So low drag at low pitches, high drag at larger body pitches. So what are the energy implications of this behavior? The metabolic rate for this fish has been measured at 4 milliwatts. The mechanical cost, energy cost of overcoming drag at 0 degrees pitch is simply force times velocity, or the drag force of 2 millinewtons times the typical swimming velocity, hunting velocities, which is 0.3 milliwatts of mechanical work or energy power needed to overcome the drag. That's 8% of the total rate. At 30-degree pitch, it goes up significantly, up to 20% of total. That's a big jump for an animal in the amount of energy you invest in movement. So change from neutral to pitch posture doubles the rate, doubles the relative cost of movement conservatively, and the observed behavior is half as efficient as it could be. How does this behavior affect information acquisition bit rate? We've answered this question. It's a big impact. What's the impact in terms of information acquisition? Well, I'm going to simply assert and not argue at the moment that one way to think about bit rate in terms of sensory envelopes around animals is given by this a formal approach called occupancy grids from robotics. Here's a headlight beam in a dark environment. You can tessellate the environment or voxelize it, and then count whether or not you detect an object within there. And of course, if it's in the sensory volume, you will. And then as that's being swept through the environment, you can think of a bit rate occurring because of that. And the larger the volume is sweeping through the space, the higher the bit rate. So that's the sense in which I'm going to use bit rate, and we can discuss it more in the discussion if needed. So how do we come up with that for the electric fish? This is not a trivial task. One approach is the empirical approach, which is put the things that it likes to go after all around the body and see where it can detect them with some sort of threshold on that. So we've done that. I'll show you the results of that. But it gives a very sparse volume. So to get a really nice, clear picture of the full 3D volume, we go to a computational approach, and we have an electric image model of how images are formed on the surface of the body. We know the addresses of all 18,000 receptors on the body. It has a particular layout with density much higher in the head and on the dorsal region and lower on the sides of the body. We have an electric field model. We have a model of the Daphnia magna, an electrical equivalent model of the Daphnia magna. And then we have a behavioral model based on all our motion capture data from prey capture studies. And we simply run like 800 trajectories where we compute voltage histories at all 17,000 receptors, and then compute spike trains based on a very accurate model of the afferent firing dynamics, the sensory neuron firing dynamics, and then put this through an optimal estimator to figure out when, probabilistically speaking, the animal is likely to detect its prey. So that's an enormous amount of computation. It takes some weeks to run on a cluster. I should say, for those of you who do computational modeling, as you know, it's very easy to get out what you want with such a complex model, but all of the parameters in the model were fixed by past publications. There are no free parameters in the model. So what we get out is this amazing omnidirectional sensory space. And so what that surface indicates is where the animal is able to first detect the prey that it's hunting. We also have the empirical sparser volume here. Part of the reason for its sparsity is we put the prey in from the top of the tank, and quite frequently it captures it before it goes any lower, and so we don't have detections down here because it's a very good hunter. Now, that's the sensory volume. We can do some clever manipulations of the motion capture data to look at where this body can move over certain delta t's. And what I'm showing here is what I call the motor volume for, in this case, it's like 450 milliseconds. And the outer volume is where any point on the surface of the body can reach. The inner volume is where any point of the mouth can reach. The important one for subsequent discussion will be the outer volume. So this is something I'll get back to later when we start talking about choice. So to continue the analysis, the sweat sensory volume I'm going to define as the projected frontal area of the sensory volume times the distance moved. So this is Apteronotus albiforans, a species that we're working on hunting 2.5 millimeter long Daphnia. And here's what happens when we increase pitch. We go from this H to this H, and so you can see the projected sensory volume in the forward motion direction of motion is significantly higher. And note that this is parasitic upon the morphology of the sensory volume. So for a visual animal, this is stone Morocco hunting a Daphnia as well, and this is a visual hunter. And here, pitching the body has no benefit to the animal because the aspect ratio of the sensory volume does not favor pitching. But we found 30-degree pitches. Why stop at 30 degrees? Why not go the full way and go 90 degrees. And so now the swept sensory volume would be sine of 90 over the sine of 30, or 1.9 times bigger as a result of that orientation. And so your first thought would be, well, you can't generate force that way, but I'm going to show you, in fact, it can generate force very well that way, and it does move in that direction. So that's very interesting. But in any case, the bottom line is the observed behavior scans the environment at half the bit rate it could. So the overall picture is the mechanics are lousy, and the sensing is also lousy. And so is there something going on here that could be interesting? Well, let's first look at how projected sensory volume changes with pitch, and then we'll look at energy. But the way if we just idealize the sensory volume as a cube, we can easily calculate the projected sensory area as W times the length of the sensory volume times the sine of the pitch angle plus H times the cosine of the pitch angle. Easy. So here's how the projected scan area in the direction of travel varies as a function of pitch angle for 3 different body shapes. The actual case, the natural case, an elongated version of the natural case, and a cuboidal version. And you can see that just as there's not much benefit conferred on the visual sensorium to pitch, that you can see that for the cuboidal aspect ratios, you have very little benefit with increased angle. For our guy, there's a maxima at around 63 degrees or something, and as you get more elongate, it's even better. So an elongated sensory volume is favored. And what's curious about this is that something that ichthyologists have wondered for a long time over the 180 species of these animals that live in the Amazon is these are extreme morphologies. This is the anal fin of the animal. Normally the anal pore is just anterior to the anal fin. So what's happened is the anus has been pushed all the way up to this point in these animals. And in fact, the entire body, all the intestines and everything is confined to this tiny little area, and all the rest of this is basically housing the electric field generator. So in extreme morphology, elongation has always been a question why. Perhaps we have some insight into it, because the field generator runs from the base of the skull all the way to the tail, so your sensory volume is essentially your body shape. So let's think about energy now. How does energy change as a result of pitching the body? I showed you that drag data. We can integrate the two things to see how these things work together. So we have our projected sensory area, SA, here. The distance then to reach a single prey. So what we want to do is understand how much energy does it take to reach a single prey item. So the distance to reach a single prey is going to be 1 over the prey density times the reciprocal of the projected sensory area in meters. The time to reach that prey will be that distance divided by u, the velocity of the fish. And then we can, drag goes up with the square of velocity, and there's a simple linear function that's a prefix of that quadratic relationship that's easily fitted to our empirical and computational drag data, so that way we can look at what is the drag given any given pitch of the body. I'm sorry this is slightly cut off. The P power for thrust will then simply be F drag times the velocity of the fish. So we substitute in F drag, so we get G theta times U cubed now. And then U, we can solve for U, and then we can solve for the energy to reach a prey given a value for thrust power, which I take from the empirical data at some reasonable value, times d over u, and that works out to this equation finally. Okay? So now we have a relationship we can look at. What is the energy to a single prey as a function of all these things, including projected sensory area as a function of pitch? All of these things are empirically established. The only thing is prey density is hard to find for rivers of the Amazon. I found a few papers, but largely varying numbers. So I did run a sensitivity analysis, and nothing I'm going to tell you depends on a particular value of this. It just shifts the curves up and down, and it's not the absolute value of the intercept that matters. It's the relationship of the qualitative features of the curve that matter. So here was our scan area. Here's what the energy to reach prey story is. So this is largely solving much of the mystery. In the blunt case, it basically goes up immediately as soon as you pitch the body. In our case, it goes down, and there's a minima, the energy needed to reach a prey at around 50 degrees. Not 30, 50, so we'll get to that. And it gets even better as you get more elongated. But there's a 35% decrease in energy needed per prey if you're pitched at 50 degrees versus 0 degrees. So this is an interesting thing, but we do have a little bit more work to do. So why is it 30 rather than 50 degrees? And so now I have to tell you a little bit about the thrust mechanics of the ribbon fin. So now we're going to go to the moving boundary case. Again, run on a supercomputer at 6,000, Reynolds number of 6,000. Essentially, the fundamental mechanism for the generation of thrust is, and these are velocity isosurfaces, this poltergeist-like green goop. And it's being basically like a paddle wheel being shuffled down the ribbon fin. But if you take a vertical cross-section of the ribbon fin, you can see that it's also doing this at the same time. Now what that does is it shoots fluid down. You can see little bits of isosurface going down there. And that generates a force as well. But now it's a heave force, not this direction, which is a surge force. And that heave force turns out to be significant for something later. So you've got this sort of picture. You've got a force mechanism here and a force mechanism there. And now another feature that has been mysterious about knifefish for a long time suddenly becomes very clear, is that this angle of fin insertion, not body pitch angle now, but the angle of fin insertion is almost always 10 degrees. And what we find in both our simulations and now in our robotic results I'll show you shortly is that at optimal wavelengths on this fin, the relationship between the surge and heave forces is around 10 degrees. So this is how the animal maximizes its thrust in the forward direction. Interestingly, the African electric fish that has no common ancestor with this fish has evolved also an elongated morphology and also a similar angle. So we've done, not happy with the simulation result, just doing simulations, we've also done a bunch of robotics work. This is the inside of the robot with an American quarter for scale. There's 32 independently controlled motors on this, so we can do very complex waveforms. And here it is swimming in an air tunnel, in a water tunnel, I should say. You can possibly see some particles going by. It's extremely stable, so it doesn't look like it's moving at all. But in fact, it's moving at about 30 centimeters per second right now, suspended from a frictionless air table. All right, so as we pitch the body as a proxy for pitching the fin, because we're not clever enough, we could design a mechanism where we could adjust the pitch of the fin independently of adjusting the pitch of the body. But as we adjust the pitch of the body, we get the following relationship between speed of the robot now and pitch angle of the robot. And it's peaking at around the values you would expect based on the simulation results and based on the morphology we see of these animals, which again is 10 degrees or so. So wrapping all together the quantitative analysis of thrust, which we've now got a very good quantitative model for, with the empirical data, we're actually able to estimate the total thrust as a function of pitch angle. And what you see is that there's a 30% decline at 50 degrees of pitch, which was the optimum from purely the energetic standpoint. So we haven't integrated this stuff back into energetics yet, but you can see that there therefore be a pressure to go to lower pitch angles to maximize thrust. All right, so we have a hunting mode for this animal, pays some drag costs, energetic drag costs, to get better bit information acquisition rates, and we have a cruising mode where if it's trying to get between patches of food, it's obviously going to pick the energetically favorable method for movement. Now, so the conclusions of this part of the talk will then be that the metabolic cost of information combined with the energetics of movement can give significant insight into problems where informational and mechanical constraints are being met at the same time by an organism, which may frequently be the case in behavior. Second, restricting inquiry into neuronal systems or mechanical systems alone in these cases would have resulted in a failure to understand. Specialization of knowledge can put brakes on cracking the Baroque complexity of animal life. So let's quickly think about the basis of omnidirectional mechanics. I want to show you this one result we just recently published. The waves not only go in a single direction, they can actually start at both the head and the tail and meet in the middle. And why would the animal do this? Well, it's very complex to get this animal to do it when you want, and it does it quickly and for these non-periodic maneuvers. So we put the robot in a laser illuminated tank and some particles, and we shone some light on the particles, and here's what we saw. So you see this beautiful jet forming. So the reaction force is going to push the animal up. So it can actually swim in a vertical direction. And that's interesting because the top of the animal's, the dorsum of the animal has this higher sensor density. It frequently is popping its body up very quickly to reach its prey. And this is the mechanism by which it does it. And here's just another view, pseudocolor enhanced, of that jet just to see how well structured it is. We've done some computations on this, and we've shown that, in fact, the momentum transfer rate is very efficient. It's recovering most of the momentum from those two jets with that redirection. And we just published, this is a cover story from last month's Journal of the Royal Society interface. So I've been thinking for some time now, working with these issues in mechanics and neuronal systems, how can we put these two systems together in a conceptual framework that's satisfactory? What is the computational potency of the non-neuronal part of the body? We often think of all the heavy lifting of a body being done by an animal's nervous system, but maybe that's not quite right. My favorite example of why that may not be quite right is this thing called the passive walker, which has no motors. It has no electrical connections. It simply has joints and masses that are oscillating due to some energy input from this inclined plane. And you can see that the pattern of movement looks extremely similar to our own gait. So in other words, something you would think of as requiring a lot of neural control, our basic gait pattern, actually comes for free from passive mechanics. Of course, you need this grad student there holding him occasionally. So what's going on there? Well, that's where the nervous system comes in, because to deal with things on short time scales, you need things like brains, which have time cycles of a millisecond set by the biophysics of neurons, to react to things like slight misadjustments in gait and things like potholes in front of you. And so, but really, we should think of the entire span of the organism as doing computational heavy lifting, with bone and chitin in invertebrates, which costs very little energy, doing as much as it can for the animal on the time periods that are relevant, and then brain doing what it has to do. And so we can think of a bone-brain continuum of plasticity to the environment. So now I want to talk about how sensory and motor volumes are related and how they're evolved, what their evolved relationship tells us about behavioral complexity and choice. So here's a special motor volume, the motor volume that is related to the reaction time of the animal. Okay, so every animal has a reaction time related to conduction delays of its neurons from its sensory periphery to its central processing structures. So we can ask, what is the volume of movement it's going to take before it can react to any of its sensory inputs? And this red volume is that, and I call it the stopping motor volume. And now we can compare the sensory volume to the reaction time motor volume in different cases. I distinguish between three different modes. The collision mode, in which the stopping motor volume is larger than the sensory volume. A reactive mode, in which the sensory volume and the motor volume are similar in size. And then a deliberative mode, which I think is very special, in which the sensory volume is vastly larger than your stopping motor volume. Now, why and how did we evolve the deliberative mode? Clearly, we are higher acuity visual creatures that can see far further than our reaction time motor volume. Why and how could that have come about? Well, here's the situation for both visual predators and electric predators, almost all predators in the oceans and fresh waters. Their sensory volume is only slightly bigger than their motor volume. Basically, they're in reactive mode. They go through space. They hit a predator. They have to react. There has to be simple transformations from sensory data to motor output. They have no choice in that. And here's a situation for an animal in a deliberative mode. You have a large sensory volume now, small, same size reaction motor volume. And now you can look at several behavioral options for the future. And here's where choice might come into relevance here, is that if you could put A, B, and C in working memory and select the max over the likely fitness of these possible trajectories, then you actually might have a reason for evolving deliberative mode, because you can see that these different trajectories will clearly have different payoff values. If this is a herbivore with a high acuity visual system, if you disclose your position early, you're not going to get that herbivore. If you have to go through the pool of water, you're not going to be in good shape by the time you get there. But if you stalk along this line of bushes and then chase this animal over this short distance, you're likely to catch it. So here is what we need in terms of an evolutionary approach to why we would have evolved deliberative modes, which is that here's a fitness payoff that selection can work on if we had the right environment for this. And so what is the right environment for this? Well, it turns out that in fluids, the attenuation length of light in fluids is around on the order of tens of meters. In air, it's essentially infinite. It's 100 kilometers, which is beyond basically usable range by an animal. So simply by emerging from the water 350 million years ago in the Upper Devonian, using the same wetware with some slight tweaks to the cornea, you can get this mode almost immediately, which is very interesting because now the animals that might have evolved working memory and choice over those options would have had big selection advantage over those that did not. And so this brings me to this quote by psychologist Bruce Bridgman, who said that consciousness is the operation of the plan executing mechanism, enabling behavior to be driven by plans rather than immediate environmental contingencies. Now, this isn't all that we mean by consciousness, but I would argue that it's a clear enough definition to get us going on some practical tasks, and that include why would we have evolved a mechanism to decouple us from immediate environmental contingencies, and I'm giving you a reason that that might have been the case. So there's one simple test that we can look at. This is probably overly simplistic and probably wrong, but there's one simple test that we can, at least wrong in some ways. It seems overly simple, but one simple test we can do is we can look at eye orbit size in fossil animals pre-emergence onto land and compare that to eye orbit sizes, relative eye orbit sizes post-emergence onto land. And of course, if the theory is correct, they should be larger post. And I'm very happy to say they are. And I'm now I'm going to be collaborating with the discoverer of this fossil and the discoverer of this fossil to do measurements on their fossils and some others, peri-terrestriality, to see if the pattern holds up. So to really go off into the stratosphere on this point, it's interesting to me to think about, this is an approach to understanding limits of our existence on the planet in terms of various forms of perturbation to the planet. And we've exceeded boundaries, according to a large number of geoscientists, on 3 of these dimensions. And it's interesting to think about whether, to some extent, our difficulty in handling awareness or being aware of long temporal and spatial contingencies might be partly rooted in the evolutionary history of our awareness. So one final thing, this is I'm fortunate to be funded by a Presidential Early Career Award, which requires an outreach project. And oftentimes when I tell people that I work on electric fish, they say, do they come with batteries? And So I've been trying to think of a way to maybe raise people's awareness over the contributions of this animal to our understanding of the brain. Over 3,000 papers have been published on the neural systems of these electric fish, and we understand a lot about our own brain as a result of them. So we built this system that I'm just going to play a short video that explains what it's about.
Scale is an interactive installation that features 12 electric knife fish from the Amazon River. The fish comprise a choir made up of 12 different species. Each fish produces a constant electric field, and each species has its own characteristic frequency. They use their fields to detect their surroundings and their prey while hunting. Those fields are picked up by custom-built sensors and then amplified. The signals are then routed so each fish is given its own channel and speaker for a spatialized sound experience. Arrays of LEDs under each tank provide visual feedback.
These sonified electrical fields provide the source tones for an immersive audiovisual environment. Participants act as producers using a touchscreen interface. Each interactor can cue an individual fish or combine the sounds of several fish together. The fish are housed in individual tanks sculpturally arranged in an arc with a podium in the middle. Each fish can be heard unprocessed or with digital effects added, with immediate control over their volume. The resulting sonification of each fish can vary widely in pitch, depending on the species, falling within the range of 30 to 1700 Hertz, from the lowest B natural on a piano to the G sharp key 6 octaves higher.
So this piece debuted at the Stripe Art Fair in Eindhoven in November of last year, and 30,000 people had fun playing with it, and it just finished a run at the National Art Museum of China in Beijing, where 100,000 people played with it. So it's been a lot of fun, and I'm hoping to get some curators interested in the US, possibly even in Chicago, Nick Pritzker, and we'll see if I could meet some curators that would enjoy this piece. But, so this is the first electric fish composition. I sort of wondered if people would do things more John Cage-like than 80s covers of Duran Duran, and I was wrong. And here's the first tune that people did. Oh, I need to do this again. Oop.
Scale is an...
Okay.
Ready?
So the first electric fish composition. So I have many collaborators to thank for this work, especially Nilesh Patankar, who's a brilliant computational food mechanician with whom I developed some very efficient algorithms for simulating these animals in fluids, and many others. Thank you very much.